Hello. In this problem, we are going to solve an open steady system, a water heater. Here is water coming at state 1 and leaving at state 2. A lot of information is given to us, and let's go over them. First of all, the pressure is 150 kPa and temperature 70 degrees Celsius at the exit. The volume flow rate supplied here. The inlet temperature is also given. Atmospheric temperature is given, and some heat loss, 2 kilowatt heat loss from this water heater is also given in this problem. We'll try to find various quantities. This is from chapter 4 in your textbook, and also chapter 6 covers open steady problems. So all the theories can be found there. The problem can also be located as an example problem in chapter 4 in the problems module. If you go there, click on examples, and the solution is unrestricted. That means you can click there, you can see the manual solution, and also you can see the test code posted here, which we are about to produce. So let's get started. The correct app would be if you click on TESTapp and follow the test tree. It's quite obvious. It's a system analysis involving open steady system. It's a generic system as opposed to special purpose system. And it's a single flow system because there is only one flow flowing through that water heater. The model to use would be a SL model. It's given in the problem. So we click there. And here are all the examples, videos, and test codes. But the left tab launches the app. Okay, so let's start entering the data. State 1 is our inlet. You just click anywhere on this property to turn it on, to put it in the input mode. 150 kPa is the SI unit already there. Temperature is given 15 degrees Celsius. Okay, it's chosen already. So to expedite the video, I've already calculated state 2. I'll just show you what I've done here. So pressure doesn't change. There is no friction, so I substituted P2 equals P1. Temperature was given at the exit to be 70 degrees Celsius. I put that in. And of course, mass flow rate doesn't change. And you can calculate the state fully with this information. Let's go set up the device panel now. We go to the device panel. State 1 is the inlet state, and state 2 is the exit state. And there's a heat loss given to us, which is minus 2 kilowatt. A calculate will produce the answers. And to find the energetic efficiency, we can go to the I/O panel. And there we can start writing user code. What it means is to calculate auxiliary variables, I can declare, let's say, for example, J dot required in kilowatt. That is the amount of heating that is going on is shown by the increase in flow energy, which is m dot 1 times J2 minus J1. So if I hit enter or just click the calculate button, look, it has been calculated. So we can, the work required is basically the electrical work input, and their ratio is the energetic efficiency tool. I have already done that in another tab, so I'll take you there. So as you can see, J dot is the amount of energy gained by water, and this is what is supplied. W dot required is minus W dot external. If you recall that external work, if you go back to the device panel, is negative because work is going into the system. That's the electrical work going into the system. So to make the ratio a positive quantity, we put a negative sign here. So this ratio of the two is the energetic efficiency in percent. Of course, we have to multiply by 100. So this illustrates how we can extract variables out of state panel, device panel, and create new auxiliary variables or results of the problem. What I want to show now is how to isolate parameters so that we can do a parametric study. So for that, what we'll do is Again, I'm starting from there, and notice the same solution. So for instance, here the pressure is given 150 kPa. This is a hard input here. But in the I/O panel, we could go isolate user codes to get rid of the clutter. And we can say, the parameters given, let's put them before this block, because these are my auxiliary variables. So we can declare a variable. Suppose we can say pressure in kPa is 150. Remember that this has to be in SI units. So for instance, now I can go and this will not be registered unless you click calculate here or there, doesn't matter, the same button. You can see that pressure has been calculated and reported here, 150 kPa. Even if you put any other unit, doesn't matter, it will be always regarded, treated as kPa. Any information entered on I/O panel will be treated as SI units. So now that we have declared pressure as a variable, instead of hard coding it, we can write down here equal P kPa. Now if I calculate or super calculate, for instance, to make sure you have the same answer, go to the device panel, see the answer hasn't changed. So in the state panel, the pressure that I entered, if you move the pointer over, you can see what value is picked up. You can see it's P1. Just keep an eye on this area. That's where the variable will show up. So if I go over P1, you can see it's shown as 150 kPa, which is correct. Now let's go and define the temperature, and I want to make sure this is, again, the user code comes after test code. You can click use isolate, and that removes the test code. You can click the super calculate to regenerate all the codes in a nice format. So okay, so here if I hit shift enter, then I can put a new line, or you can take away enter as calculate to enter a new line. So you want to introduce temperature at the inlet in Kelvin, which will be what? It was given in Celsius in 15 plus 273. Well, approximately, it's really 273.15. That's a very small difference. So if I do a calculate, T inlet Kelvin is found here. And if we go to the state panel, now we can substitute equals T inlet in Kelvin. If I do a calculate, then the state is recalculated, but you always go to check, move the pointer over, and see it's shown in Celsius, pretty close to 15 degrees Celsius. So this unit is basically the output of that. If you say Kelvin, then it will be shown in Kelvin. If you say Celsius. So in other words, what you are putting here, the equation equals T inlet K, will be picked up from the I/O panel, and you want to make sure the temperature is in Kelvin. All right, so likewise, I can isolate all the variables, in which I have done here. Isolating parameters, so as you can see, the pressure, all the variables given in the problem has been explicitly specified here. So now we can go and substitute all of these variables inside, which I have already done. So you can see that now, if I can go through the code, see the pressure, temperature are given. Actually, the volume flow rate also we should be substituting. My bad, it should be the variable, this one, volume flow rate in meter cube per second. So if we come back to the state panel, so let's take the hard code away and put equals this. So this will be always picked up the correct value, but it is always a good idea to check that you calculated it correctly. So if you put the pointer over, see, you can see the volume flow rate in meter cube per second. If you change it back to liter per minute, that should be 10. Yeah, that's 10 liter per minute. So we got the right variable here. If you do a super calculate, all the test code and user codes, first comes the test code here, which tells you what we have done, state 1, how we calculated state 2. And even the device panel, we have substituted Q.1, which is a variable with sign as minus q dot loss being 2 kilowatt, and surrounding temperature as T surrounding Kelvin. And we got all our answers. In the I/O panel, in the bottom, you can find the efficiency, energetic efficiency, etc. at the bottom, which is 95%. Suppose the question is, how will the answer change if the heat loss were 4 kilowatt? Look how easy it is now. Because we have isolated all the variables, we can do a what-if study with any of these variables. So heat loss was 2 kilowatt here. So all we'll do is change that to 4 kilowatt. First, we'll click calculate because that has to be registered. So now heat loss has been registered, 4 kilowatt. The bottom panel is what the computer sees, and this is what you enter. And now to refresh all calculation, we click the super calculate button, and everything is calculated now. If you go to the device panel, you can pick up the work required, the external work or electrical work. And in the I/O panel, you can see the energetic efficiency will be changing now from 95% to 90%. So in other words, once you develop the test code with user code producing isolating all the variables of the problem, essentially you can play with this problem and change a parameter and find its effect on the problem, on the solution. Hope this helps to build any other solution in this manner, in a robust manner.